Okay, so what I want to teach you today is how to add. That's to say, I want to teach you how to add in enough detail that you might sometime be able to make a machine that adds. And I hope people are ready to believe that adding things up is something that computers do all the time. You know, your shopping cart when you do some online purchasing. So being able to make machines that add up is an important thing. You wouldn't be able to cheat on my homeworks by using a calculator to add stuff up if the calculator couldn't add up. So fine, nice bit of freedom there. And let's start with the simplest kind of adding problem, where, let us zoom out, where we're going to add up two values which are as small as possible but still interesting. That's to say, two 1-bit values. So the numbers we're going to add up are either going to be zeros or ones. So if our two inputs are 0 or 1, what's the smallest possible value that our total can take?
0.
0. And if they are 0 or 1, what is the largest possible value that their total can take?
3.
If we're just adding two of them, then 1 plus 1 in arithmetic, rather than 1 or 1 in logic, is 2. So we're going to need to be able to represent numbers in the range 0 through 2. How many bits will that take us? That'll take us 2 bits. And just as we write decimal numbers with a ones column and a tens column, if we're writing 2-bit binary numbers, there's a ones column and a twos column. So I had some questions about what ones and twos are supposed to mean in the homework problem involving a 7-cell display displaying numbers in the range 0 to 3. When I write ones and twos as column heads, I mean the ones column of that number and the twos column of that number. So for example, the number 2 would be represented in binary as a 1 in the twos column and a 0 in the ones column. That's all that's going on there. Okay? So let's see if we can muster powers of arithmetic to figure out what the answer ought to be. So we're trying to add this up. This circuit is called a half adder, by the way, which I often abbreviate to HAD with 2 Ds. So what is 0 plus 0? It's 0. How do we represent 0 as a 2-bit number?
0,
0, 0. Right. What about 0 plus 1?
1.
That is 1, represented as a 2-bit number.
1, 0.
Careful now. It's 0, 1.
Oh.
Now, how about adding 1 and 0 the other way around? Same answer. And now, don't lose the bottle at this stage. Adding 1 and 1. 2, otherwise known as 1, 0. Okay, we're doing well. Here's the thing. Here's the thing about adding up. When you take the inputs, they are a bunch of digits that have place values. And when you take the outputs, those digits also have place values. So both of these inputs had place value 1. Place value is just telling you how you should interpret a 1 in this column. A 1 in this column is worth 1. A 1 in this column is worth 1. Whereas in the outputs, a 1 in this column is worth 1, and a 1 in this column is worth 2. So you can see that the total place value of the inputs is always the same as the total place value of the outputs. Only the outputs looks like a number, whereas the input looks like two numbers. So what we've done is, we've taken two numbers in, we've sent one number out, we've preserved the total place value of everything. That's what adding is. Okay. Next up, we need to learn to build one of these circuits out of actual bits and pieces, right? Logic gates. So let's see how to do that. We've got two inputs coming in. Let's call this one X and this one Y. And two outputs coming out, 2s and 1s. And if you please, keep the 2s to the left of the 1s, the way we do when we are writing numbers. Okay, so let's look at these two. We've got to produce effectively two circuits, one for each of the outputs. And we can see their truth tables. If you look at the 2s column, does that ring any bells? Right. Someone is beginning to learn their truth tables backwards. That's excellent. If you see this column, it is exactly the truth table for AND. So what that tells us is that we should just stick AND here. And wire it up like that. All right. Right. So this is supposed to be computing whatever comes out here.
The table for one's NOR.
It's not NOR. It's close though. Yeah. So this is AND. And this is XOR. You can see that we get a 1 out when we have either a 0 or a 1 coming in, but not both. So that's to say, this is telling us whether the output is odd. It's doing an odd or even thing. Yeah? So that's the truth table for XOR. So let's put an XOR gate there and wire it up again to the same two inputs. And I know this diagram is perfectly clear because nobody has told me that it isn't. So if anybody complains after the lecture that it was unclear, I'll know they were lying. All right. This is all very well, except that we need to know how to build XOR. So let's just think about how to do that. Some people have been asking how to build XOR. Let's be systematic about that process. Here's the universal trick for reading a truth table and building a circuit that does the same job. You look for the rows where the output is 1. Yeah? So for our XOR, that's this row. And I'll do the other one in red. This row. So I have selected the two rows where the output is 1. Now we can see which bit patterns of the inputs produce those outputs. And we can build detectors for those bit patterns. So we can have a detector for the bit pattern 0, 1, and a detector for the bit pattern 1, 0. Those are the bit patterns we are interested in. Does everyone see why? They're the ones that give us a 1 out. Now, remember how to build a detector for a bit pattern. You turn the zeros into knots. And the 1s into wires. wire them together with AND. So we've got two detectors. We had better make sure that their inputs come from the right places. So X wants to go into the left of both of those, and Y wants to go, this is X, Y wants to go into the right-hand input of both of those detectors. So this detector will give us a 1 exactly if the inputs match this row. And this detector will give us a 1 exactly if the inputs match this row. We want a 1 to come out in either of those circumstances, so all we need to do is OR those detectors together. So there you are. That's how you build a circuit when you can see a truth table. You build a bunch of detectors for the bit patterns that deliver an output of 1, and then you OR them all together. Which is another way of saying that you build a disjunctive normal form for the problem. What is an OR? What is a disjunctive normal form? It's a big OR of a bunch of possibilities. Each possibility is given as an AND of a bunch of conditions. And each of those conditions is either a variable or its negation. That's to say, it's an OR of detectors for bit patterns. All right? So now we know how to build a circuit that adds two 1-bit signals. So actually, in general, the place values, well, I mean, it would be awful if we could only add bits that had a place value of 1. Then we couldn't make very big numbers. But in general, the place values for the inputs will be 2 to the n, and the place values of the outputs will be 2 to the n and 2 to the n plus 1. That's to say, if you're adding 2 bits with place value 2, you will get an output where the 2 bits have place values 2 on the right and 4 on the left. And the same thing all the way along. And one terribly important thing to remember when you're building circuits that add stuff is that you should only ever add bits with the same place value. Otherwise, you're not really making sense. That makes it a good idea to be aware of the place value of the signals that you're working with. So we shall often label the wires in arithmetic circuits with place values. And apart from that, there's not much else to add in.